to everybody. Welcome back. We proceed to this 3.2.2, which is state space representation. Okay, you can see here we have what we call state equation. So we are going to represent this one in this form. So we're going to have we need to write in this form: x dot equal to ax plus bu, and then we can see what will be the output of it, which is y equal to cx plus du. So this x, we have here the variable here x, which is a state variable vector, and then we have here y. Okay, this is x, this is y, this is x. X is a state variable vector, and y, see, this x is a state variable, and then y is the output vector. Okay, y is the output vector, and u, can see this u, one u, this u. Question 3.3 also we have u. 3.4 also have u. So u is an input vector. Okay, we have output vector, you have input vector, and then we have here the state variable vector. Okay. All right, next one, we proceed to the important part of this topic, which is transfer vector. Okay, transfer vector is the ubat, sorry. So we have a transfer function. Okay, transfer function, TF, transfer function. So transfer function, you can see here, is related with Laplace transform. It's a ratio of Laplace transform of the output, okay, and the input by assumption, but assuming that initial conditions are 0. So initial condition, we make assumption all 0. Okay, so we have here transfer function of y as, okay, output divided by the input. Okay, so we have ys divided by us. Okay, these are the general form that we can write. Here b dot b1 b sn a dot s, and then an minus 1. These are the general form on how to write the transfer function. Okay, all right, this is degree of freedom, number of degree of freedom, generalized form. Okay, so when people say number of degree of freedom means the number of independent generalized coordinate that specify the configuration of system. Okay. Okay. Now we proceed to 3.3. Okay. Since we are going to be, all of you going to be mechanical engineer, I think all of you already familiar with the mechanical system, been exposed in previous subject, and then static, dynamic, and vibration, okay? Theory, and practically. Okay, so we start with the one that we're familiar with, which is mechanical system. Okay, so we proceed with the first one, mechanical system. mass and inertia element. Okay, so we have here the diagram of it. Okay, using Newton's second law. You know that Newton's second law, F equal to mass times acceleration. This is Newton's second law. Newton's second law. Okay, so you have a force here, and then you have force over there, and then you have you can see mx double dot there, okay, and force, and then we have the inertia here, okay, angle theta, okay, moment equal to I dot theta double dot, okay, this is mass and in inertia element in mechanical system, okay. So we have here, still recall, you still recall, we have translation, translate, and rotation. Okay, translate from here, from A to B, right? Point A to point B, in straight line, translate. And then at the same time, you can rotate. Rotate will involve an angle. Okay, rotate. Okay, from A to B. So it rotate. Okay, certain angle. So you have translation and have rotation. So based on this diagram, mass and element, initial element, you can see here, you can resolve summation of force here into x and y, right? X and y. So you can see here the way we can write is summation force mx double dots, okay, and then for y you're going to get my double dot, y double dot. This is for translation. Okay. How about for rotational? For rotation, this is summation of force. Summation of force. Okay. And then this is summation of moment. Okay. Summation of moment. So summation of moment, we talk about the rotational motion. Okay. So you will have this one. So summation of moment equal to I dot theta double dot. Okay. So still remember this equation? What is the name of this equation? You remember? Anybody?
Parallel axis theorem.
Remember, good. This is parallel axis theorem. Yeah? Good. Parallel axis theorem. Okay. So you substitute this I, okay, using parallel axis theorem, and you get equation 10. Okay. So from here you're going to get M and then D, okay, and then theta double dot. Okay. All right. This is for mass and inertia element. Okay, they have translational motion and rotational motion. Right. Next one, we proceed to uh, spring element. I did mass, mass. We proceed with spring and then damper. Okay. There are different types of spring. Excuse me. We have linear spring. In the market, we have different types of spring. Okay. Ada yang leaf spring. Kalau big truck dia using leaf spring. Ada torsional spring. So for linear spring, the basic concept is very simple. Which is we have this is for 1 degree of freedom. We have spring force. Okay, this is a spring force equal to kx. Kx. So in this case, the load, it will be directly proportional to the deflection. So once you stretch the spring, it will go back to its original position. And you will have also here the k. What is k? K is spring constant. Okay. So for a linear torsional spring, okay, this is for torsional spring. And this one again for 2 degree of freedom. We have 2 degrees of freedom. This is 1. This is 2 degree of freedom. So you can write the system to be as the following, which is k times x2 minus x1. Yeah? This is spring force of the spring. Okay, for torsional spring, it involves theta, right? So we have torsional spring Kt equal to Kt theta, right? But for 2 degree of freedom, we're going to get K times Kt mean torsional spring minus T theta, okay, which is torsional, right? This is for spring element. How do we represent it? Mass done. Now we have we did for spring. Now we proceed through for the damper. Okay, damper. Some people say use different word of what damper. They use it as a dashpot. Okay, dashpot. So the function of dashpot, the damper. Anybody know in the spring mass system? What is the purpose of damper? Anybody want to share? What is the function of it? Hello? Anybody there? Anybody home?
To absorb shock, sir.
Okay. Any other answer? Most of you have motorbike, you have a big bike, have a car, right? So what is the use of the damper?
To compensate
To compensate.
the vibration.
Okay. The right word is, I think, to absorb. Yeah. Example of it. Okay. All right. That's why the physical meaning is very important. Physical meaning. Do not look at the equation simply like you solve the mathematical problem. Remember, you as an engineer, you need to should be able to explain the physical meaning of it. So for translational 1 degree of freedom, nampak? That's why saya tulis untuk damper nampak force. Tadi force spring kan? This is force damper. Force damper. We write force damper. Kalau torsional pun sama, torsional damper. If spring, we write spring force. Simple lah. So every notation tu subscript ni it carry different meaning. So the elemental equation for translation and rotation. So in this case, we have translation, we have rotation. So same concept lah, like what we did just now. The uh, force damper. So we can write in this form, which is C x dot. Okay. So kalau 2 degree of freedom, we can write C, okay, x dot minus x1 dot. For the case of torsion, you can have a, okay, torsion, and then theta dot, okay. Then this one you will have theta dot 2 minus theta dot 1. So this is what we call a typical element, typical type of damping element, okay, in a mechanical system. Okay. So we have done these three lah. Okay. Recap balik apa yang kita tengok tadi. We have mass and inertia. Mass and inertia. We have summation of force and then summation of moment. Summation of moment. And then we have another one is spring element. Okay. So spring element we have transitional spring force, and then we have torsional. Okay, this is how you write. And then another one is a damper element. Okay, damper element. Somehow you got same thing. We have damper force for 1 degree of freedom system to translation, and then we have 2 degree of freedom for translation also, and then we have torsional. Okay, same thing. Ada translation, and then we have torsion. Okay, torsional system. All right. This one again, you're familiar with, you have taken design 1, right? Design 1, design 2, right? Design 1, you learn about gear, right? How to calculate gear, speed ratio, tangential velocity. So kena buka balik lah buku design, tengok balik. Because this class is control class, so you should be able to use that concept, okay, and relate in this class. Nampak sini ya, we have here, okay. This is the just recap what you have learned before. We have the definition of speed ratio, okay, speed ratio, and d1 divided by d2 divided by d1, and this is speed ratio. And then you also have tangential velocity here. Okay, so how to find tangential velocity? We have vt equal to r t dot 1 equal to r2 theta dot 2, okay, theta dot 1 theta dot 2. Then we have also here tangential force, okay, tangential force, which is the ratio of d1 divided by r1. R is d1 over 2. So t2, we have here t2, and then the ratio, the radius, which is d2 over 2. Okay. So we have theta 1, and then d1 divided by d2. This is speed ratio. You're going to get theta. Okay. All right. So the two gear rotate. They oppose each other and will give the relationship of speed ratio, tangential velocity, tangential force, etc. Okay. Just to refresh what you have learned before. Next one is equivalent system. For a system with gear. Okay. This is how we can write. T2 is J theta double dot 2 and then you can T2 is NT1, and then T2 also NT1. You can relate with NT1 equal to J over N theta double dot 1. Okay, so going to be T1 equal to JE theta double dot 1. This is just a brief explanation. Now we want to go through work example 1. Okay, I hope if time permit, you can go through all of these examples during this tomorrow. Tomorrow is your another lecture. So I think you can go through this work example. Okay, in detail. We look at this example 1. We have 2 degree of freedom system, and then we want to express the governing equation in configuration form. Okay, nampak keyword here in configuration form. Okay, the one that we need lah for the system. Okay, configuration form. Okay, so you're familiar with this one. We have schematic diagram for 2 degree of freedom. Remember this one. This is translational system. So we have here spring, mass, damper. Spring, mass, damper. So looks like they are flying. So they should have ada apa? Ada berpijak di bumi lah. Ada bertimbang. Okay. So we have K1, K2. Okay. X1, X2. C1, C2. Okay. I think all of you remember this. We want to establish first step is the free body diagram of the system. Okay, free body diagram of the system for these two. Okay, this one we have learned in gravitation. Okay, so we draw the free body diagram. Okay, okay. So this is M1, this is M2. So you have here, this is K1, X1. So C1, X dot. Then we have N1, X double dot. Okay. Then on your right hand side, we have M2, X double dot 2. Okay. And then what happens in between is this is remember the one we did just now, the second degree freedom. So K2 X2 minus X1, and C2 is X dot 2 minus X1. Okay, this is the first step. Okay, first step. And then you apply Newton's second law. Okay, Newton's second law. Okay, Newton's second law you apply, which is summation of force equal to mass times acceleration. Okay, so what we're going to have here is mx double dot 1 equal to the summation of force in x direction. So you have k2 plus c2 x dot, this one, and then minus kx, opposite direction, this one kx, and minus minus cx, so this is equation 12. Then for the second one, m2x2, okay, m2x2 is minus, okay, minus kx2 minus x1, and then we have minus. So we have these two equations. So to apply Newton's second law, which is by using summation of force equal to mass times acceleration based on this free body diagram. Okay, based on this free body diagram. Okay. Okay, next one is the one, the next step is called, we want to write in configuration form. Okay, so to write in configuration form, we should write x double dot 1 and then x double dot 2. We need to write in this form. So need to divide this one, divide by m, m1, this is divided by m2. So you're going to get this 312 equation, we divide by m1. So you're going to get 1 over m, parenthesis of whatever value that you have here. All of the value that you obtain there. Same thing with this one, you divide by m2, you're going to get 1 over m2, all of this, you put it in parentheses. Okay, all right, so you can write in this formula, x double dot 1 and then x double dot 2. Okay, oh, it's raining already outside. So are you okay? Are you following? This is how to write this system. Okay, this system, 2 degree of freedom translational system. You want to write in this this configuration form. Okay, but I'm here not to teach you dynamic or vibration, but we would like to, after you obtain the equation, we want to write in the configuration form so that we can use it to apply in dynamic system. Dynamic system. Okay. Any comments so far before we proceed with example 2?
No.
Slowly, telan. Okay, example 2. Okay, what's the difference between example 1 and example 2? Anybody can tell me? What's the difference? Anybody tell me? Are you with me or not? It's raining already.
This one has damper.
No, the previous one also have dampers. Any other answer? Anybody want to try?
Ada external force kot.
Yes. You have the applied force, right? Nampak ni, applied force kat sini. The previous example, you don't have any applied force. Nampak? Mana ada force ni? This first example. Second example, we have subjected to applied force Ft. Okay, so you have applied force there. So we want to express the equation of motion in second order metric form. Okay. Right? That's why they said this 2 degree of freedom translational system subjected to external force. Okay. All right. So again, first step we establish a free body diagram. Free body diagram. Okay. Similar to the previous one, but we have a additional thing here. We have this. Okay. Okay. And then We apply Newton's second law and then write the equation in second order metric form. Okay. So we can write as the following. Okay. We can write in this form. Okay. So the lengthy equation that we have here, this one we can write by using metric form. Okay. You still remember how to multiply metric? Okay. So we have M1. Okay. So recall how to multiply. You should be able to know, and then how to factor this out. So M1 times X plus 0x2. Okay. So 0x1 plus M2. Okay. Same thing with this one. This one will be factored out. Okay. So you have here function ft. Okay. All right. Another example. We rewrite obtain state space from the system shown in work example 2. Okay. So we want to obtain state space. Okay. We haven't finished this one. Question example 2, we only stop at step number 2. So we proceed according to equation 314 and 315. So 314 and 315. Okay, we want to write in this form. Okay. So we would like to write in this form. Okay. So you multiply all of this. So you're going to get x1. So you divide by m. So you get 317. Same thing for x double dot 2. You divide by m2. You put everything in parentheses. Okay. Okay. And then next, define the state variables and obtain their corresponding first order derivative. Okay. Okay. So this is state variable. We define x, y, and last date. This you can see. We proceed to define state variable and get their corresponding first order derivative. Okay. So we define z and z1 until z4. Okay. To equate it with x1, x dot 1, x2, x dot 2. So we will have to substitute it. So you have the derivative of it. So z1 is equal to x1. So z dot equal to x dot 1 equal to x dot 1 is equal to z2. So z2. And then z2 dot equal to x double dot. Okay. Z2 dot is x double dot 1, which is the one above. Okay. Okay, which is this one. This is 1 over m1 a2. So you substitute x2. Okay, x2 is z3. Go to z1. So you have to substitute with the what we call a state variables. Okay, state variable. Until z4 towards the end, you are going to get 1 over m2 ft. Okay, 1 over 2 ft. Okay. And then for the state equation, which is z dot, want to write in terms of a z plus bu. Okay, so you put all together here, z1, z2, z3, z4, and then write in terms of this metric form. And then take this one to be z1, z2, z3, z4. Then everything multiplied by external force here, 0, 0, 0, 1 over m over 2. And then in this case, has been defined here, x dot, okay, x dot. This is basically x dot, okay, and this is a, okay, this is basically a, okay, and then you have here b, right? This is b. This is x, and then this is b, right? 0, 0, this is b, and then ut, okay? So it's a function of b. So this is state equation, and then we will have the output equation in this form, which is y. Remember the one that we have defined earlier? You see z plus du, okay? So y is 1 0 0 1 0 0 0, then 0 1 1 0, okay, so you can get multiplied by z1, z2, z3, and z4. So again, same thing, this one, this is c, and then this is x, okay, this is x, and for this case the value of d equal to 0, okay. Okay, this is for example for example 3, how we can write or obtain the state space of the system. Okay. Okay, this one is another example. I think I would like to stop here. Okay, stop here for today. For work example 4 is related to um, how to write the diagram for rotational system. Rotational system. Okay. Um, you derive equation of motion, you obtain the natural frequency, okay. Okay, what else is I think important to highlight? Okay, so I hope you can go through this example on your own. So in our next class, we are going to proceed to look at how to model the electrical system. Okay, so by the way, I'm going to give you a few problems for you to solve, okay, in order to strengthen your understanding. Okay, I think that's all for today. I'll see you in our next class. Thank you.